Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Moon Regolith, the cosmic dust that tells our lunar story. The moon's surface is marked by craters, mountains, and plains, tells a story of cosmic history and celestial events. One of the most intriguing aspects of the moon's surface is its regolith, a layer of loose, fragmented material that blankets the lunar landscape. This narrative delves into the fascinating world of lunar regolith, exploring its composition, formation, scientific significance, and the role it plays in future lunar exploration. Lunar regolith, often simply referred to as moon dust, is a fine, powdery material that covers the moon's surface. Unlike Earth's soil, which is formed through biological and chemical processes involving water and organic matter, lunar regolith is the result of billions of years of meteorite impacts and the harsh environment of space. These impacts pulverize the moon's surface rock into fine particles, creating a layer that varies in thickness from a few meters in the highlands to tens of meters in the Maria, the large, dark plains formed by ancient volcanic eruptions. The composition of lunar regolith is a complex mix of rock fragments, mineral grains, and glassy particles. The primary minerals found in the regolith include plagioclase, pyroxene, and olivine, which are common in basaltic rocks. These minerals are mixed with tiny beads of volcanic glass, formed from the intense heat generated by meteorite impacts. The regolith also contains agglutinates, which are clumps of particles fused together by the heat of micrometeorite impacts. This unique composition gives the regolith its distinctive properties, such as its fine, powdery texture and its ability to cling to surfaces due to its electrostatic charge. The formation of lunar regolith is a testament to the moon's violent history. For billions of years, the moon has been bombarded by meteoroids of all sizes, from tiny grains of sand to massive boulders. These impacts have shattered and pulverized the surface rock, creating a layer of debris that continually churns and mixes with each new impact. The lack of atmosphere on the moon means that there is no weathering or erosion by wind or water, so the regolith remains largely unchanged over time, preserving a record of the moon's history. One of the most significant scientific discoveries related to lunar regolith came from the Apollo missions, which brought back over 800 pounds of lunar rocks and soil to Earth. Analysis of these samples has provided invaluable insights into the moon's geological history and the processes that have shaped its surface. For example, the presence of tiny glass spherules in the regolith indicates that the moon has experienced intense volcanic activity in its past. These spherules are formed when molten rock is ejected during volcanic eruptions and cools rapidly in the vacuum of space. Another important discovery is the presence of solar wind particles implanted in the regolith. The moon's lack of an atmosphere and magnetic field means that its surface is directly exposed to the solar wind, a stream of charged particles emitted by the sun. These particles become embedded in the regolith, providing a record of solar activity over millions of years. By studying these particles, scientists can gain insights into the history of the sun and its effects on the solar system. Lunar regolith also holds clues to the history of the Earth-Moon system. For example, isotopic analysis of oxygen in the regolith has revealed similarities with Earth's own oxygen isotopic composition, supporting the theory that the Moon formed from debris ejected during a giant impact between Earth and a Mars-sized body. This finding has profound implications for our understanding of the early solar system and the processes that led to the formation of the terrestrial planets. The unique properties of lunar regolith pose both challenges and opportunities for future lunar exploration. One of the main challenges is the abrasive nature of the regolith, which can cause significant wear and tear on equipment and machinery. The fine particles can infiltrate seals and joints, leading to mechanical failures. During the Apollo missions, astronauts experienced firsthand the difficulties posed by the regolith, with the dust clinging to their spacesuits and causing problems with equipment. Developing materials and technologies that can withstand the harsh conditions of the lunar surface will be crucial for the success of future missions. Despite these challenges, lunar regolith also presents opportunities for resource utilization. One of the most promising applications is the extraction of oxygen from the regolith, which could be used to support human life and produce rocket fuel. The regolith contains a significant amount of oxygen bound in silicate minerals, and various methods have been proposed to extract this oxygen, such as chemical reduction and electrolysis. The ability to produce oxygen on the Moon would reduce the need to transport large quantities from Earth, making long-term lunar missions more feasible and cost-effective. In addition to oxygen, lunar regolith contains other valuable resources, such as metals and helium-3. The regolith is rich in metals like iron, aluminum, and titanium, which could be used to build infrastructure on the Moon. Helium-3, a rare isotope of helium, is of particular interest because it has the potential to be used as a fuel for nuclear fusion reactors. The Moon's surface contains a relatively high concentration of helium-3, implanted by the solar wind, and mining this resource could provide a valuable source of energy for future generations. The potential for utilizing lunar regolith extends beyond resource extraction. The regolith could also be used as a construction material for building habitats and other structures on the Moon. The concept of using in situ resources to construct lunar bases, known as in situ resource utilization, ISRU, is a key focus of current research and development. Techniques such as 3D printing and sintering, which involves heating the regolith to fuse particles together, are being explored as ways to create durable, self-sustaining structures from the lunar soil. These methods could enable the construction of habitats, landing pads, and other infrastructure, reducing the need to transport building materials from Earth. The study of lunar regolith also has implications for planetary science beyond the Moon. Understanding the processes that have shaped the regolith can provide insights into the geology and history of other airless bodies in the solar system, such as asteroids and the moons of other planets. The techniques and technologies developed for studying and utilizing lunar regolith could be applied to future missions to these bodies, advancing our knowledge of the solar system and its formation. As humanity looks to the future of space exploration, the Moon remains a central focus. The Artemis program, led by NASA, aims to return humans to the Moon and establish a sustainable presence by the end of the decade. The study and utilization of lunar regolith will play a critical role in achieving this goal. By leveraging the resources and knowledge gained from the regolith, we can pave the way for long-term lunar exploration and lay the groundwork for future missions to Mars and beyond. In conclusion, lunar regolith is a fascinating and complex material that holds the key to understanding the Moon's history and unlocking the potential for future exploration. Its unique properties, shaped by billions of years of meteorite impacts and solar wind exposure, provide a record of cosmic events and offer valuable resources for supporting human life and exploration. As we continue to study and explore the Moon, the regolith will remain a central focus, guiding our efforts to unlock the mysteries of the cosmos and establish a sustainable presence on our celestial neighbor.